Hello and welcome. In this video I'll be going through the solutions for the Chapter 6 test review that has topics such as finding indefinite or definite integrals using either a substitution approach, an integration by parts approach, or potentially even just doing improper integrals. So let's go ahead and jump on in. For number one here, it just wants us to do a pair of indefinite integrals. So for part A, we'll just start with trying identifying something potentially that I could do to get the ball rolling. So this one seems like, since there's a function inside of another function, that a u substitution likely will work, so we'll just give that a try. So whatever's inside of that function, in this case the square root, would be a good start for what I should maybe try to let u equal. So that makes the du equal 2x dx. So notice I do have the x, I do have the dx, I just don't have the 2 that I need. So what I would do is just create the 2 by multiplying and dividing technically by 2. So out front I'll just call that 1/2. And kind of simultaneously in the next step I'm going to go ahead and move the 5 that was in there out front with that 1/2 that I just created. So altogether this will now turn into, once I do that substitution, 5/2 now outside. Again, as mentioned, this 5 I'm just moving out front with the 1/2. And then on the inside, the 2x dx, all of that collectively will get to be turned into du at the end. And then the square root, I'm going to go ahead and just rewrite using an exponent. Remember, a square root is the same as a 1/2 power. Now it should be a relatively straightforward power rule problem. So I would just add 1 to that 1/2 and turn that into 3/2. And then dividing by 3/2 recalls the same as multiplying by its reciprocal, so multiplying by 2/3. At this point we can also introduce the plus c and hopefully see that the 2's, where I have one on top, one on bottom, will actually get to reduce, leaving me then a 5 times this u to the 3/2. So I'm going to go ahead and do that back substitution, switch back to x's. X squared plus 9 is going in place of the u, and then the 3/2 is the power on that parenthesis, and then only thing that's left on the denominator since the 2's canceled is the 3. And then I still have my constant at the end, so plus c. Alright, moving on to now letter B. Letter B is going to be a similar approach. I'm going to need to do a u substitution. In this case, what seems the most logical is to let the u equal whatever's inside of a grouping. So in this case, the x minus 2 that's being raised to a power 4. Unfortunately though, the du for that is just going to be a dx, so that doesn't really replace this x that's in the numerator that's being raised to a power of 2. So our approach in that scenario is actually going to be just rewrite this u, where I could picture like I could move the 2 the other direction and ultimately turn that into an x value equaling u plus 2. So from here now, if I go ahead and do those substitutions, and I'm going to go ahead and just draw a little barrier so we don't accidentally get those confused, but this first one would now turn into, if I replace the x in the numerator, a u plus 2 being squared, and then the denominator is going to become a u to the 4th, and then the dx turns into the du, as we hopefully could see with our substitution. Now our goal from here, what we're kind of forced to do, is expand out that power in the numerator. So if I go ahead and apply that power of 2 to everything, it would be a u plus 2 times another u plus 2. So first term would be a u squared. My middle terms would be a pair of 2 u's, which combine to give me 4u. And then plus at the end 2 times 2, which would give me a 4. And then all of that still would be over the u to the 4th. But why that's nice is when there's just a single thing in the denominator, I actually can split up the numerator and simplify. So that's actually what we'll do in the next step. So if I think about dividing each of these 3 terms in the numerator by that u to the 4th, the u squared will just turn into a u to the negative 2. The 4u is going to turn into a plus 4u to the negative 3. And then the last one, I could just rewrite that 4 being divided by u to the 4th as 4 times u to the negative 4. That way we can kind of get this set up to where we can just do a couple of power rules that are hopefully relatively simple. So each of these, now I'm going to increase my power by 1, then divide by that result. In this case it would be u to the negative 1 over a negative 1, added with a 4 u to the negative 2 over a negative 2. So that looks like that one will get to reduce here in the next step. And then the next one would be a 4u to the negative 3 over a negative 3. and technically plus a constant. So at this point, kind of running out of room vertically, so we'll just move that up here to the top right and actually kind of do kind of a combination of not only dealing with the negative exponents and maybe reducing, like that middle one, the 4 over the negative 2 can reduce, but also we may as well at this juncture replace all of the u's back with what we said u was, which was the x minus 2's. So this collectively would turn into, it looks like a negative 1 would stay in the numerator, and then I have u to the negative 1 drops to the bottom, so that's just going to be the x minus 2 on the bottom. Next one, 4 over negative 2 is now a negative 2, so I'm just going to leave the 2 in the numerator, and then I end up having the u drop to the bottom but becomes squared, so x minus 2 quantity squared. And I'm already kind of squishing myself here as well, but this one would become now more a minus 4 on top, and then the denominator would end up with a 3, x minus 2 being cubed, and then there would be a plus c. So let's see if I can maybe write this a little bit cleaner here in the next line. So negative 1 over x minus 2 first term, minus a 2 over x minus 2 squared for the next term, minus a 4 over a 3x minus 2 cubed, and then plus a c at the end. And there we go. Now number 2 here is going to have a very similar approach to what we just did with letter B. Again, more than likely trying a substitution strategy at the beginning. It's just this time, because it's actually a definite integral instead of an indefinite, I may also have to worry about switching some of the bounds. So like my lower limit and upper limit of that integral will likely need to change because I'm switching my variable. So for this one, if I said that u is equal to x minus 4, I could also then say that x would equal u plus 4 if I just added 4 to both sides. And then we also have that the du in this case would become dx, or sorry, yes, du will replace the dx. Sorry, I misspoke there. But now let's go ahead and figure out what those two numbers would turn into. So the 0 that I have as the lower limit, if I just substitute into this u substitution, it would become 0 take away 4, which is just a negative 4. Similarly, the 1, that's the upper limit, plug that in, I get 1 take away 4, which would give me negative 3, so I can, at this point, just stay in terms of u's for the rest of the problem because I'm switching those bounds, and then at that point I wouldn't have to really worry about switching back to x's. If I did, then I would actually want to make sure that I go back to using the 0 and the 1. So anyway, let's go ahead and do those substitutions here. So my integral now is going to have a lower limit of negative 4, an upper limit of negative 3. The x is going to get turned into a u plus 4, and then the x minus 4 that we had is going to just turn into a u, and then that's being cubed, and dx turns into du. So for this one, it's more, let's distribute that u cubed through and just turn that into a pair of terms. So I've got still my integral in front, u times u to the third would give me u to the fourth, plus, and then 4 times u cubed, doesn't really simplify at all. And now it's a pair of power rules, so u to the fourth will turn into u to the fifth over 5, plus the 4, and then u to the fourth over 4, so those two 4's will actually get to reduce, so I may as well just cross those two out. And then my limits again, upper was negative 3, lower was negative 4. So from here now it's just plug in the numbers and simplify. So if I go ahead and do those steps, it would be negative 3 to the 5th. If I go ahead and do that on a calculator really quick, turns into negative 243. And that would still be over a 5. Plus, here the two 4's again just canceled, so it's just going to be negative 3 raised to the 4th, which is an 81. Minus, now plugging in negative 4 to the 5th. Looks like it gives me negative 1024 over the 5. And then negative 4 raised to a power of 4. That actually will make that positive 256. So now it would just be, let's simplify each of those. So I think the first parenthesis, if I type that in, yes it does, turn into 162 over 5. Then I have minus, the second one turns into 256 over 5. And combining those things, I would end up with negative 94 over 5 as my final result. Now for number 3, this one wants us to go back to an indefinite integral again. So here it's telling us specifically to utilize integration by parts. So for this one, it's kind of focus our attention on what two things are being multiplied. And I've got an x squared, and then I've got an e to the 4x. So I get to kind of choose what do I want to let the u equal, as well as what do I want the dv to equal for integration by parts to really start working. This one, because of the e, more than likely that's going to be something I'll select for the dv portion. That way I can get this x squared. If I let that equal the u, that would then kind of dwindle its power down. But because it's got a power of 2, it's kind of letting me know that I'm probably going to need to do 2 cycles of this. So anyway, if we go ahead and just try letting the u equal that x squared, again, as mentioned there just a second ago, du is now going to become a power 1 less. So it's making progress, or it's going to make progress in the right direction. The dv, if I let that equal everything else, which would be the e to the 4x dx, my v then in this case would end up turning to still an e to the 4x, but I got to kind of think reverse. So instead of me multiplying by 4, it would actually be multiplied by 1/4. That way, if I did do the chain rule derivative of the v, the 4 that would result on the outside has something to actually reduce down to a 1 with. So kind of the shortcut here working backwards is if I ever have like e raised to something that has more than just an x, or the x has a coefficient on it, it's just going to be the reciprocal of that coefficient that I'll need to put out in front. So like in this case, the reciprocal 4 is the 1/4, hence where the 1/4 is coming from. Anywho, now we're going to go ahead and follow the pattern for integration by parts. So just to maybe put that underneath, remember the pattern is u times v minus the integral of v times du. And I have all of those parts identified, so I'm just going to do that really quick right underneath it. So my u times v, it looks like is just going to become an x to the 4th, or sorry, x squared times e to the 4x, there's where the 4 is, all over a 4. Then minus the integral of, I'm going to go ahead and just keep all of this inside. It looks like I've got 1/4 e to the 4x, but also a 2x dx. So that 2 and the 4 will actually get to combine together. So let's maybe clean that up just a little bit. But as mentioned just a little bit ago, I will likely need to do an extra integration by parts step. In this case, notice I can make the 2 and the 4. If I divide those two, it just turns into 1/2, and just kind of move it out front so it gets a little bit out of the way. And now we'll just need to do that second integration by parts for the most recent integral. So here we'll just let the u equal the x, which makes du just dx, and then that makes the dv have to be everything else, which really is the exact same as what we just did. So since we already have done the work, we know it's just going to turn into a 1/4 e to the 4x for the v. And then follow that integration by parts pattern again, but we can't forget this term that was out front, the x squared e to the 4x all over 4. That's just going to hang out there until the end. Now because I have this coefficient of minus 1/2 in front, I'm going to go ahead and just put a parenthesis around this integration by parts pattern, the uv minus v du, just to remind myself that I will have to distribute that negative 1/2 through. And now let's go ahead and figure out what each of those things would be. So similarly, at this time it's just going to have an x times e to the 4x over a 4 instead of the x squared like it was before. And then minus the integral of, I've got 1/4. Technically I could probably just move that out front, but I'll leave it inside just to kind of show where it technically exists. And in the next step I'm going to distribute through so we can maybe do that combination step. So if I go ahead and eliminate those parentheses, see what that would turn into. I've got x squared e to the 4x all over 4 still out front. This first term now is going to have an x e to the 4x in the numerator, but now a negative 2 times 4 gets me a negative 8, so that's just going to be the minus 8. And then the double negative on the next one is going to actually switch that to addition. And here I've got 1/8 in front, still times the integral of e to the 4x dx. But we've already done that one actually twice. So I'm hoping this is not too overly complex. This will be x squared e to the 4x over 4 minus the x e to the 4x over 8. And then the last one, the e to the 4x will turn into another 1/4 e to the 4x. So the two denominator numbers of 8 and 4 will get to multiply together and turn into just a 32. And then e to the 4x is just going to hang out on top. So I could write this in a little bit different format since all of those had an e to the 4x. I could maybe factor that out front. I also could try and approach this where I try and figure out what a common denominator would be, which looks like it would just be a 32 if I really wanted to, and factor that out at the same time, but I don't require that, and I don't think it's really all that beneficial to go ahead and do that. But just to kind of point out, there are a couple of different versions that this answer could be left in, but I think this is the one that is the easiest for most of us to get to, so may as well just leave it there. For number 4, this one's going to be another integration by parts, but this time it actually is a definite integral, so I'll actually, instead of having the plus c at the end like the previous example, I'm going to go ahead and actually need to plug some numbers in. This one, though, I notice right at the beginning, we've got an x to the 4th, and we have a natural log of x. That kind of forces our hand into letting the u, sorry, I'll try and stay color coordinated here, having the u just be the natural log, because I don't really have an integral for natural log, but I do know the derivative. So that is kind of the only thing we can really do, is just go ahead and let the du, the u be the natural log of x, so I can get the du of 1 over x times dx, and then everything else must just be the dv. So for this one, it would be x to the 4th dx, and integrating that going backwards would become an x to the 5th over 5. And now I should be able to follow that pattern just like we had in the previous example of, again, the u times v minus the integral of v du. Now, I'm not technically switching my variables. Notice everything still is staying in terms of x's, so that's where this is a little bit different than the substitution example we had earlier, where I won't have to switch the 1 and the e to anything. So that's kind of nice, at least with regard to this question, is I can go ahead and just keep those as is without having to do that extra step. So let's go ahead and figure out what this will turn into. So the u times v looks like I could write that as x to the 5th times the natural log of x. Then all of that would be over the 5 that the v had in the denominator. And then minus, I'm going to go ahead and just kind of factor that 1/5 out again because of the over 5. And then on the inside it would just be x to the 5th times the 1 over x times the dx. So the x to the 5th over the x that technically is inside there will actually get to simplify. So let's go ahead and just show what that would turn into. The x to the 5th times the natural log of x all over 5. Sorry, I forgot to keep my bounds on that as well, so it should have a 1 and an e there. Then minus the 1/5 integral from 1 to e, like I needed it to be, but x to the 5th over x will actually simplify down to an x to the 4th. And now it's just going to be a power rule for that one. So x to the 5th natural log of x over 5 minus this 1 over 5, x to the 5th over 5 again. So I could technically combine that. Let's just go ahead and do that and call that a 25 in the denominator. And now it's going to be substitute in a e first and then substitute in a 1 second. So if I go ahead and do that, I think I might have enough space here, hopefully. E to the 5th would be our first one. Then I'd have natural log of e would become natural log of 1. Or sorry, a natural log of e has a value of 1, so it's just e to the 5th times 1 over a 5 minus an e to the 5th over 25. And after that, it will be minus what happens when I plug in 1. Well, the natural log of 1 will just turn into 0, so this whole first fraction is going to be a 0. And then the second one I'd have just minus a 1 raised to the 5th, which stays 1 over 25. And at this point, it looks like I can probably just get a common denominator of 25 by multiplying the top and bottom of this first fraction by 5. That gives me 5 e to the 5th, take away 1 e to the 5th, for a total of 4 e to the 5ths. Then I still have the minus a negative, so switch to addition by 1, and all of those were over 25, so I'm able to combine them together. And voila, there we go. We've got our value. Moving on to number 5 now. Number 5 wants us to just utilize partial fractions. What's actually semi-nice about this is it's already in a factored form in the denominator, but if we look ahead to maybe like what number 6 is that you can see on the screen, we'll likely need to factor the bottom of that one before I split it up. I do need to make sure it's in proper form, so this is a proper fraction because the numerator does have a smaller degree than the denominator. So I can't go ahead and off to the side just do my setup. So I'm just going to rewrite in the factored form what this one's starting with, but set up the two fractions that I want it to split into. And here I'll just utilize a and b, but technically you can pick whatever letters you would like. So if I now go ahead and multiply everything by those two factors, that should give me an expression that no longer has any fractions. So again, here it looks like the x's for sure would cancel, the x minus 6's would cancel, leaving me for sure that 3 equals, next one it looks like the x's would cancel, leaving me the x plus 6. So I'd have a times x minus 6. And I always just said plus 6, it should be minus 6, my apologies. And then the last one, the x minus 6's cancel, leaving me just the x. So it would be plus b times x. So now I just choose a couple of numbers to let my x equal. So I'm going to go ahead and just choose, let's let x equal 0. That should let me solve for the a value. And that new expression then would be 3 is equal to 0 minus 6 is negative 6 times a. And then divide the negative 6 over, which gives me now an a value of negative 1/2. Similarly, if I do a, let's let x equal positive 6, that should let me cancel out the a, or that would zero that out. My new expression now would be 3 equals 6 times b, and dividing the 6 over gives me a b value of 1/2 that's positive. So if I go ahead and substitute that in place of the original, I can now rewrite it as those two fractions added together. So the a, which was negative 1/2, was over just the x, added with the b, which was over the x minus 6, and then make sure that it's all grouped up times the dx to close off my integral. So from here, these should just turn into natural log integrals. So I've got my coefficient of negative 1/2 that's just going to kind of hang out from the numerator. The derivative, or sorry, not the antiderivative of the 1 over x that would be left with now would be the natural log of the absolute value of x. And then move on to the next one. It's going to have that same general concept of the numerator is going to be the coefficient, and then natural log of whatever the denominator is, and then plus c at the end. And at that point, if I had done any substitution, I'd back substitute, but no need to do that here. There are a couple of different versions we could do. There is a way that we could find a way to combine these, but again, I'm not going to require that on the test, so why do some extra work if we really don't necessarily need to? I just need to see that you understand how to do the decomposition first, and then also how to actually integrate once you've done that split. Next one's going to have a very similar approach. So number 6, as kind of mentioned in the previous one, I probably want to picture like what this is in factored form. So that quadratic in the bottom would get to turn into an x minus 4 times an x plus 1, because that's what would multiply to the negative 4 at the end, but add to the negative 3 in the middle. And at that point, we can maybe off to the side just set up our decomposition. Since again, this was already a proper, I didn't have to do any long division or anything special like that. But I'm going to go ahead and just split it up and put the a over, I think I'll just put it over the x minus 4, and then the b over the other one, x plus 1. And similarly, if I go ahead and multiply everything by those two denominators, that would just leave me a negative 4 on the left side. The x minus 4 would cancel, but the a would still need to get the x plus 1. And then the second one, the x plus 1 would cancel, but it would leave the x minus 4. So you can kind of just hopefully see that that pattern there is really just one factor cancels in this case, since there were only two, and it leaves the other one on each other expression. So now I go ahead and just let x equal a couple of different numbers. In this case, I'm going to start with the x equaling 4. That way I can solve for a. So that gives me negative 4 is equal to 4 plus 1 is 5a. So that tells me that a must be negative 4/5. And similarly, I'll let x equal negative 1 to cancel the a term. Let me solve for b. So here I get negative 4 is equal to negative 1 take away 4 is negative 5b. And dividing that negative 5 over, I get b is equal to positive 4/5. So kind of just more coincidence than anything else that those two values have basically been opposites with these last two examples, but they don't necessarily always work out that way. Just again, like I said, sheer coincidence. Now, another difference about this problem is this one is actually a definite integral because it's a true area from 0 to 3. So when it comes to setup, I now actually have some bounds of integration, my lower being 0, my upper being 3. But I can now just substitute in those two values that we just had. Negative 4/5 would be over the x minus 4, since that was the a, and then my b was over the x plus 1, so positive 4/5 will go there. And just like the last example, those should just turn into natural logs when I actually do the integration step. So this would be negative 4/5 times that natural log, the absolute value of x minus 4, added with the 4/5 times, this time it's the natural log of the absolute value of x plus 1. And last example would have been a plus c at this point, but now I actually have those bounds to plug in. So let's just go ahead and get those numbers substituted in and see what they turn into. If I plug in 3 take away 4 would give me negative 1. Absolute value of negative 1 would actually turn into positive 1, and natural log of 1 will always just turn into 0. So that's actually semi-convenient for the first one. Then it's going to be plus the 4/5 times natural log of 3 plus 1 would give me 4. Absolute value of that would just stay a positive 4, so we know that that's just going to be a 4/5 natural log of 4. Then it's going to be subtract what happens when I plug in 0. So here I'm going to get a negative 4/5 times the natural log of 0 take away 4 is negative 4, but its absolute value is positive 4. So that turned into a positive number. And then the last one, similar to what we had to start, 0 plus 1 will be 1. Natural log of 1 is just 0. So I can go ahead and say that also equals 0. So now it really looks like I just have a couple of natural log of 4s, both with coefficients of 4/5. I do have a minus and negative situation, so those actually will add together and become 8/5 times the natural log of 4. And that's really as much as I need to. I think if you did this on one of the calculators, they might break the 4 down to 2 squared and move the 2 out front. So this also could be like 16/5 times the natural log of 2 on the calculator if you wanted to double check. But just to explain the y is technically that 4 is 2 squared, and then powers, remember, can move out front and then just multiply, so that's why the 8 would double and turn into a 16. Okay, so both of those would be acceptable, but I assume most of us would be just okay leaving it as a 4 like it was there. All right, now on to the last one here. Number 7 just wants us to do a couple of improper integrals. So remember, the approach with these improper is to just pick a letter to replace the trouble part. In this case, the infinity is the issue with this first one, and just replace it with that letter. And then I'm going to go ahead and just rewrite this as a negative exponent to make it a little bit easier to evaluate. That 2 as a coefficient is just going to kind of hang out for a little bit, so I'm just going to leave it inside because it's not that big of a deal to deal with. And now it's just going to turn into e to the negative 4x will stay, but then I'd end up having to multiply by the negative 1/4. So the 2 technically would be over a negative 4 eventually in the next step. But again, it's not a plus c situation. This is actually a plug in some values. So for this one, it would be, now let's go ahead and maybe simplify, but also plug in the b. I'm going to now drop it back to the denominator, so I've got the limit as b is approaching infinity of the 2 over negative 4 would reduce to a negative 1/2, and that would be a now 2 on the bottom, and then e to the positive 4x, still where I'm going to be plugging in b first and then 0 second. So let's go ahead and do those two things and see what the limit would become if I let the b go to infinity. So it looks like the first term would just now be negative 1 over 2 e to the 4b. Then I'd have minus, and then negative 1 over 2 e to the 0 would just become e to the 0 is just a 1. And let's close off all my parentheses appropriately, which now I can go ahead and say that the infinity on the first one is going to make that turn into 0, minus a negative switches to addition, and then 2 times 1 on the bottom would just stay at 2, which gives me a 1/2 as my final answer. Now for part B, we have the issue of 9 creates an undefined value in the denominator. So what we'll have to do is create the limit as a variable. I'll just choose b again for this problem. Approaches that number, but specifically since it's the upper bound, it'd be from the left. And now I should be able to now simplify or replace that 9 with that b but also rewrite the inside using 9 take away x being raised to a negative 1/2 power times the dx. So this one, because that's more than just an x, I would have to do a u substitution like an earlier problem, or the first two really in this video. So if I let du just equal that 9 minus x, I'd end up with my du would become negative dx. So I would have to, for this example, create a negative 1 to make that substitution work. And now go ahead and continue on, where I can now replace each of those values. And actually probably go ahead and move that 2 out front with the negative 1. And that now would become u to the negative 1/2 du. So if I go ahead and integrate from there, and I could, if I wanted to, switch my bounds, but I'm going to go ahead and just keep it as is, and just switch back here in just a moment to x's. It'll still be approaching the 9 from the left. I still have the negative 2 as the coefficient. U to the negative 1/2 would turn into u to the positive 1/2. Then divided by half is the same as multiplying by the 2 over 1. And again, my limits here, b and 5, but remember those are x's, so I do have to switch back to x's before I can do the substitute in step. So for this one, I got a negative 4 that looks like would stay in front, and then replace that with 9 minus x. And I could rewrite that using a square root symbol instead of having the 1/2 power, but does not really matter. I'm just going to simplify each of these here in the next step, and then apply the limit. So if I go ahead and do that, I've got the 9 still from the left that I'm approaching. I've got negative 4 that's going to multiply by 9 take away b inside of a square root, so negative 4 square root of 9 minus b. And it would be minus a negative, so that would switch to addition of 4 times 9 take away 5 to the 1/2, and then simplify. So I'll scroll down just a little bit here and get that we can have the limit as b is approaching 9 for the first one. 9 take away 9 would be 0, so this really was just going to turn into 0, plus 4 times 9 take away 5 is 4. Square root of 4 is 2, and if I go ahead and simplify that, that gets me my final answer of 8. So hopefully that was helpful for this specific problem, and hopefully the video here has helped prepare you for the test. But as always, if you have questions, just come find me and we'll see if we can sort it out. But anyway, I appreciate you taking the time watching the video, and we'll catch you next time.